Okay, let's talk about GE2. So on this problem, the idea is, well, the first thing we have to do is draw a picture of what our set looks like, right? Because we have to decide how many different pieces does it get broken up into. And so, well, here we go. Well, first of all, what does this first inequality look like? X squared plus y squared minus z less than or equal to 0. Well, by the way, no, that's equivalent to saying that z greater than or equal to x squared plus y squared. And I know what it looks like when z equals x squared plus y squared.
Yes,
that's a paraboloid. So z greater than x squared plus y squared is going to be sort of the region sort of above that paraboloid. Does that make sense? So this inequality here describes that region.
Anything on the surface? No.
Yeah, on is allowed because it's greater than or equal.
Okay.
Yeah. So the surface is included. Yeah, that's right. Okay. All right. Now the next surface is, let's see here, z minus x minus y minus 4 less than or equal to 0, which I can rewrite as let's see here, z less than or equal to 4 plus x plus y. Now, again, ignoring the inequality, if I look at the equation, z equals 4 plus x plus y, that's some plane. Mm-hmm. And it's, let me just draw some plane, whatever. Some plane there. And z less than that means I'm looking at the part that's below that plane. So altogether, the set that's described by these two inequalities is everything that's above the paraboloid but below the plane. So effectively, this plane is kind of cutting through this paraboloid, and I want to look at the part that's below that plane, but it's going to be sort of capped off by that plane in some sense, inside of the paraboloid. Okay. So let me draw a better picture. Now my picture's all messed up. Better picture, based on what, so I can sort of kind of see what I've got in there. So here's now hopefully a better picture of it. So something kind of like this. And there's this flat top there. Does that make sense? Okay. So now, having the picture, I claim I can break this up into chunks, and there's going to be 4 chunks. There's this sort of flat top surface that I'm going to call, I guess I'll call it S1. Right. Then there's the curved surface, the paraboloid surface on the bottom. I'll call that S2. Now there's also that curve where they intersect.
Yeah.
Right. And then of course there's the solid region R on the inside. So there's going to be 4 separate little optimization problems here. Okay. And on each one, you just got to identify what's the appropriate constraint on each one of those and play the appropriate game. So let's go through some of those. So let's start with in the interior region. That's the easiest one. So so in R. All right. Well, the points in R are unconstrained. Right? They're not on a surface. They're not on an edge. They're just right in the middle. So all directions are tangent vectors. You can move any direction you want. So in order to eliminate something, all you have to write down is the gradient non-zero? And therefore the only points we can't eliminate are critical point test for unconstrained points. In other words, on that interior is just set the gradient equal to 0 and solve. So I'm going to write down gradient of f equals 0. Now, of course, the gradient of f is 1, 1, 1. Okay, all right. So this is really easy algebra. Under what circumstances is 1, 1, 1 equal to 0, 0, 0? Never. Okay, so no critical points. There are no critical points in the interior. Okay, so that's done. We're okay. 1 down, 3 to go. Okay. Okay. All right. Let's try the top surface. Yeah. Let's try the top surface. So that's S1. Okay. Now on that top surface, we've got a constraint. The constraint is that I'm on this plane. that.
Yeah. Oh, yeah.
You see what I'm saying? So that the equation of that plane is z minus x minus y equals 4. Is the equation of that plane, right? Okay, so I'm going to call this my first constraint function, g1. Well, okay, yeah, anyway, g1. That's fine. So g1 is equal to 4 is my constraint equation there. And so the Lagrange condition is, it's a single constraint, so I'll write down the single constraint Lagrange equation. Gradient of f equals lambda gradient of g. And I want to solve, can I solve this little system of equations?
So,
Well,
just curious, sir,
yeah.
why do you put the 4 over? And
Because I'm gonna. It doesn't matter. I probably shouldn't have done that. It does. First of all, it doesn't matter. It really doesn't, because all I'm going to do with this function is take derivatives of it. In which case, the 4 is going to go away. It doesn't matter.
But it wouldn't be wrong to just try to 4 over.
Yeah, probably if I had it to do over again, I'd just call this whole thing G1, and the equation of the plane is G1 equals 0. Yeah, yeah, that's right. Anyway, so let's write this down in more detail here. The gradient of f, we've already agreed, is 1, 1, 1. But you can see from this formula for G1 that the gradient of G1 is negative 1, negative 1, 1. Now, I claim that there are no solutions to this. There is no way. Because the only possible solution would require that lambda would have to equal to 1, but it would also require that lambda would have to equal to negative 1. And this is not possible. There's no way. Right? So, boom, no critical points on S1. Does that make sense? So, again, the bad news on this problem is that, there's 4, there's 4 separate optimization problems. Each one has got stuff you got to do, but look how easy this one was. Oh, now, by the way, I made a mistake here. Shame on me. I didn't check the degeneracy. This was the Lagrange condition. But I need to check but the degeneracy also goes really easy here. Degeneracy, I need to look for where is the gradient of g equal to 0. Well, the gradient of g is negative 1, negative 1, 1. That never happens. So there's no degenerate critical points either. Right. So yeah, there's 4 problems, but look how fast. Some of them just go boom, boom, boom. They just fall down, Okay, let's do S2. So let's see here. I'm kind of running out of... Anyway, so S2 is down here. It's this surface. Okay, and let's see here. So the constraint is that x squared plus y squared minus z is equal to 0 on the surface of that paraboloid. Let's write that down. So x squared plus y squared minus z equals 0. I'm going to call this G2. Or I guess maybe I could have called it H. Okay. Let's call it H. All right. Let's call it H. I think that's what I did in the book now that I think about it. Okay, so H, all righty. Let's for good measure, let's write down what the gradient of H is. We're going to need to know that in a second anyway. Gradient of H is, it's 2x, 2y, negative 1. Okay, so let's play the game. First, let's do degeneracy, because we really should have done that first anyway. The degeneracy is, where is the gradient of H equal to 0? And in other words, where is this equal to 0? Answer, it's never equal to 0. That coordinate's always non-zero. So there's no critical points. The Lagrange condition is, gradient of f equals some multiple of gradient of h. Okay, so gradient of f, it needs to be some multiple of the gradient of h, and this might work.
Yeah.
Okay, so now this is easy though. It's not that bad, because check it out. I know lambda is negative 1.
Oh, yeah.
And if lambda is negative 1, that means that negative 2x is equal to 1. So x is negative 1/2. And similarly, y is equal to negative 1/2. And Now, keep in mind, I also need my point to be on my constraint set.
Yeah.
So, is this point, or this isn't really a point, by the way, but I need to find the corresponding point that's actually on my surface. Here's my constraint equation. So you can just plug in and solve for z, and z ends up being let's see here,
1.
it's a half.
Yeah.
So we have found a critical point.
I'll need to check if that's critical.
Yeah, so we're going to put that aside for the moment, but yeah, we'll eventually check the value after we've found all of our critical points. Remember, our big strategy here is the absolute maximum on our whole set has to also be the absolute maximum on whatever piece it falls on, which means it's got to be a local maximum on whatever piece it falls on, which means it's got to be a critical point on whatever piece it falls on. So I'm just going to find all the critical points. The absolute maximum is going to be in there somewhere, and then I'll just compare values.
Okay, cool.
Right. Okay, so we found one. All right. None there, none there. We did find a Lagrange critical point on S2, and now all that's left to do is to check the curve for critical points. All right, so this takes up a lot of paper. Okay. On the curve, well, I have two constraints. There's G equals, okay, and again, I made this weird choice. I don't know why I did that. But G is, hang on, Z minus X minus Y, that has to equal to 4. And H, which is, oh, here it is, X squared plus Y squared minus Z has to equal to 0. I need both of these to be equalities to be on the curve. Okay. All right, well, I'm going to need to know both of these constraint gradients, and conveniently I've already computed those. This is still -1, -1, 1. This is still, 2x, 2y, -1. So let's check degeneracy. And now degeneracy, when you have two constraints, there's a lot to check there. You have to check first, is that ever equal to 0? And nope, it's never equal to 0. Secondly, that's never equal to 0.
You have to check the parallel.
That's right. That's right. Now you got to check where is gradient of G a multiple of the gradient of H. And here, this might work. I mean, we got to be careful here. But so let's write it down. So -1, -1, 1, some multiple of 2x, 2y, -1. So I know lambda is -1 because of that. And if lambda is -1, that means that x and y are both a half. Yeah.
Yes.
And what does that tell me about z? Okay, well, wait a minute. Now, keep in mind, points that I find by way of this algebra have to satisfy both of these equations. So you're going to ask yourself now, wait, how do I solve for z? Do I solve for z in this equation, or do I solve for z in this equation? It's got to satisfy both, and I claim that you can't do both in this case, because if x and y are both a half, that means z has to equal to a half from that equation, but that then doesn't satisfy this equation.
Okay, gotcha. Not on G.
Yeah. So ultimately, it's it kind of looked like we'd found another degenerate critical point, but no, that's a point that's on this surface, not on this curve. And you could have gone the other way. You could have found, for these values of x and y, you could have found the corresponding point on this surface, but it's not on this surface, and therefore, again, not on the curve. So ultimately, there are no. That's supposed to be a cross out, not like a variable x. No degenerate critical points on C. Cool. Okay, now we got to look for Lagrange critical points. Now, on every chunk, you always, except for the unconstrained, interior, but on every boundary chunk, every constrained chunk, you have to check degeneracy and you have to check Lagrange. Yeah. Okay. So let's see, the Lagrange condition is gradient of f is some multiple of the gradient of g plus some other multiple of the gradient of h. In this case, that becomes 1, 1, 1 equals lambda negative 1, negative 1, 1 plus mu 2x, 2y negative 1. That's a y. Okay, that's a negative 1. I'm being sloppy in how I'm writing this. Shame on me. All right, and so now again we play the game. But we also have to have g has to equal to 4. Let's write it down as z minus x minus y equals 4, and we also have to have x squared plus y squared minus z equals 0. So we've got 5 equations and 5 unknowns. And look, this is always a by hook or by crook kind of deal. Here's what I notice. First off, this will not always work. But if you look at these 2 equations here, those tell you that x has to equal to y.
Yeah.
Right? Excuse me. Or that mu might equal to 0. You have to be real careful with that one. You remember that example we did in class?
Oh yeah, we have to
right?
do cases.
Yeah, we're going to have to break it down into cases. That's right.
We always have to do cases, pretty much. When you're presented with math problems where you have like a series of unknowns.
Well, yeah. I mean, that's right. I mean, you do always have to break it down into cases. Well, let me rephrase that. In a situation where you have a product, something like this, where there really is. I mean, if you were to try to prove, if you write down this first little equation, if you write down the second equation, and if you do what you have to do to get to x equals y, somewhere in there you're going to divide by mu. And whenever you divide by something, you are ignoring the possibility that it might be 0.
Yeah.
So you then have to consider that separately. So, all right. Well, now, good news. Mu can't be 0.
Oh, yeah.
Because look at this. Look what we have. If mu was 0, we'd have garbage, nonsense. This is insanity, right? So, good news. Don't have to worry about that. Does that make sense? Okay. Whew, that was good. I was a little worried about that. It was going to be a lot of work to, and just keep your eyes open, and wherever you find yourself, ask yourself, see if you can look for the little lucky breaks like that.
Could we say mu is equal to negative 1? No. Sorry. Because I saw. Oh yeah, I was doing the last time on the. Sorry.
Yeah, it's hard to know.
Yeah.
I don't think we can draw that conclusion.
Okay.
Yeah. But we can now conclude that x has to equal to y, because mu is not allowed to be 0, and therefore we can divide by it as needed, and therefore x equals y. Does that make sense? Because these 2 equations are identical, except for one has x, one has y, and therefore, yeah. Okay. So, all right. Well, now if x is equal to y, I can look at these. Now I've got 3 equations and 3 unknowns, and I can solve and see what I get. Well, okay, so I get, so z is equal to 4 plus 2x. Z is also equal to 2x squared. So therefore, 2x squared is equal to 4 plus 2x. You got a little quadratic equation here. And are we going to get lucky on this one? Let's see here. Well, let's write it out. Okay, so 2x squared minus 2x minus 4 is equal to 0. X is, let's see, minus b plus or minus the square root of b squared minus 4ac. Well, minus kills this minus, and so that actually becomes 32 all over 2a. And lucky break, that's exactly 36 under the radical. So we have 2 plus or minus 6 all over 4. Okay, so that means it's either negative 1 or 2. Now we got to be careful. Is this right? I mean, what you see what I'm saying? We got to make sure that for this value of x equals negative 1, y equals negative 1. Okay, then what would z have to be? Well, z would have to be 2.
Yeah.
If x is negative 1, yeah, that's 2. Okay, so all right, so that works. And likewise, you plug in x equals 2. Z becomes 8. 8. Okay, so both of these are satisfied. Yeah, cool. All right, so we've got 2 more critical points that are on this curve. Right, so all together, let's count them up. Yeah, there's a large process here. There weren't any critical points on our interior region, nothing. On the first surface, no critical points. On the second surface, we did find 1 critical point. Let's take a tally here for critical points. On S2, I have the point negative 1/2, negative 1/2, 1/2. Okay. Now on the curve, on the curve, let's see here. Well, there weren't any degenerate critical points. We thought we did for a second, but nope, not a critical point. And for the Lagrange, we do have 2 critical points. We have x equals negative 1, y is the same thing, and z equals 2. And we also have x equals 2, y equals the same thing, 2, because again, x equals y. And then let's see here if then this becomes 8, and z becomes 8. See? So there's our critical points. Now we just have to evaluate what f is on each of these points. Our original function, what are we trying to optimize here? It was x plus y plus z, I think? Yeah, there it is, x plus y plus z. Okay, so negative 1/2 is 0 and 12. And we have a winner. Our absolute maximum. Oh, no, I did. Okay, shame on me. I do have to. There's one final little icing on the cake that I have to put on here. Oh, keep in mind, you can only really conclude that you have an absolute maximum if you know the absolute maximum existed in the first place. Ultimately, what we've done is a process of elimination. But the process of elimination only finds it if you know it's there. So what I have to say first is f is continuous, and our domain D is closed and bounded.
So that's the first thing you have to draw.
Well, you can put it at definitely notice it. When you're starting the problem, make sure that, because if you do all of this work, and then, oh my gosh, I did all this work on the process of elimination, and it turns out, oh yeah, no, my domain's not closed. Ooh, then your reasoning that's all time wasted. So yeah, I would say definitely look for it first. Make sure that it's true, and then but just make sure to write it down before you start the party. Yeah, exactly. So f is continuous, D is closed and bounded. Therefore, the absolute maximum exists, and therefore that's okay. Right. Does that make sense? It's a tedious process, but ultimately it's just a lot of little details. You see what I'm saying? So I hope, and of course I know this recording's going on for like 20 minutes. But anyway, all right. Any questions about this?
No, I think that's good.
Okay. All right.